the afternoon testing is Rafael Presentation from PG&E, and he's going to go through some testing done for PG&E system.
Good afternoon. Can everyone hear me? Okay. I'm going to be presenting a condensed version of a paper that was written by PG&E in collaboration with Schweitzer Engineering Laboratories last year, and it was presented at the WPRC in Spokane. And this paper concerns itself with how we, PG&E, go about validating our relay settings on the relays that we're now installing, microprocessor-based relays that we're now installing to replace our legacy relays. So, what are the kind of challenges we're faced with at 500 kV, or 500 kV transmission systems? We have single pole versus 3-pole tripping, high-speed reclosing, and the big one is series compensation. So first, a little bit of history. It wasn't so long ago that our transmission system, and perhaps this is true of other utilities, we had a lot of margin. And as such, a lot of the relay manufacturers and ourselves as end users were designing our relay schemes around dependability. And with dependability, you get the propensity for overtrips. But now, in today's world, things have changed. A lot of I know in our system and many others, we're operating at near capacity, and dependability has given way to security. So now it's squarely on making sure that we trip when we want to trip, and we do not trip when we don't want to trip. So how do we go about that? Testing our relays to make sure that we validate our settings. For us, the answer lies in RTDS testing. And the first thing we do when we apply RTDS testing is to develop a model, a very accurate model that's going to help us really challenge our relays. So what we do is we take our network and reduce it down to the line we're interested in, go out at least one bus, so we can capture as much of the contingencies that we need to, again, to challenge our relays. So what do we do when we're modeling? We're going to replicate the topology, and of course series capacitance is a big part of our 500 kV system. And we ask ourselves, well, what kind of protection do we have in our series caps? MOVs, do we have spark gaps? Do we have bypass breakers on our series cap? We at PG&E use bypass breakers. And one thing that's unique that I found in talking with neighbor utilities is that our line relay will bypass the series caps when we have relay action. And I've been talking to our neighbor utilities, they don't always do that. So reinsertion controls, of course you could do it automatically or manually. At PG&E, we do it manually. Another question we asked ourselves when we were putting together, or asked of us by Schweitzer, was what kind of CCVTs do we have in our system? Do we have passive or active filters on our CCVTs? That plays into the accuracy of our model. Okay, so here we have an example of how we reduced our 500 kV system to look at this particular line right here. And as you can see, we have a number of different fault locations, and we have a number of 10 total. These would be considered our static fault locations, and this would be our sliding faults, where we can go, say, 5, 10, 15, 20%. This would be sliding faults internal to the line and sliding faults external to the line. See, we have a sliding fault here. You can see that we have here no faults because it's a parallel line that has the same characteristics. Okay, so in RTDS, they're connected directly to our relays and apply the faults directly to the relays. And then they generate contrade files that provide us with analog and digital information that I'll touch on a little bit later. Okay, so how do we go? What's the testing order? Well, once we have a model that we feel is solid, we go in our case, we flew up to Pullman and worked with Schweitzer and sat down. First day, we compare the model that they developed against our steady state model and make sure that all our fault duties are within 5% of one another. If there's any issues, we'll we'll touch on those and make sure we get it down to within that tolerance. So next, what do? We do the manual test, and we really start challenging the relays. We pick out the worst case we can think of and hammer those relays. Any issues that come up now, we address them with either relay setting changes, or in some instances, the relay manufacturer may have to address an issue. Once we're done with that step, we'll move on to what we call the automation portion of the testing, where we run script files, and we basically set up the test. We walk away overnight. We run in the order of a couple of, maybe 1,000 to 1,200 faults is usually the limit that we run. We come back the next day and check on the results. One thing I wanted to kind of step back is in the back in the days, we did very little testing when we initiated replacement of relays on our 500 kV system. And I know Ed Taylor could probably tell you a little more details as to what kind of testing we did. And as we progressed through the years, we would, say, apply a couple hundred faults to challenge our relays and validate. And at this point, we're talking about upwards of 5,000 tests. And the ratio is about 4 to 1. We will apply about 4,000 external faults and about 1,000 internal faults. Okay. Oh, I need to. There we go. Okay. So these are a listing of the manual tests that we run, and one of the tests that I found interesting was this zero sequence center of line, where we put a fault on the line in question and run it until we get to the point where we get equal zero sequence from each terminal. And at that point, we will add resistance and start ramping it up until the relays at either end will no longer detect the fault. That gives us a sense of the sensitivity of our scheme. Another way we can challenge our relays is point on wave. At different points on the wave, we'll apply the fault, and that will challenge the relay with different levels of offset. So I touched on the automation portion of the testing, where we just walk away and come back the next day. And if we were running external faults that night, we'll come in and we'll start looking for any instances of trips. And if we do encounter any instances of trips, we'll zero in on those faults, run them manually, pull back events, and determine what the problem is, and either, again, revise settings, or maybe the manufacturer will have to do something on their side. And then, believe it or not, we run all 1,200 faults all over again, because it may well be that by making one fix, we create another problem. Today, we've been, I think, pretty lucky, or just good, I don't know, whereas where we simply make the fix and we move on, because we don't get any additional problems. So this is a table here that describes how we go about selecting those 1,200 faults that we're going to test on any given night. And as you can see, we'll be looking at different power flows, different contingencies where we may take out a bank here or a line out there to make the system weak or strong, and again, challenge our relay settings. Fault types, we always apply all 10. And as I mentioned before, we have about 10 different fault locations that we can run with. And of course, the point on wave that I talked about earlier. So what we pull back from our results are these discrete digital points that help us determine how well the scheme is operating. Zone 1s, permissives, reclose initiates, blocks. Those are the kind of things we're looking at to determine how well we're operating. And those get pulled back. We developed an Excel macro that will pull back all this information, which is quite extensive, and puts it in a format where we can look at it in color-coded. We can see if something's red, it should be green. We know that's a problem. We can zero in on it and, again, do more testing, revise settings, what have you. And the last point there also talks about how we also graph and get a sense for how good is our series compensation, how much zone 1 instantaneous are we getting out of our relays, is one example I can think of. So basically, RTDS testing has helped us get a very good familiarity with our relay schemes, our own relay schemes, and those of the manufacturers. Our models become very accurate, and we can reuse those down the line as we go through and start replacing relays on adjacent lines. Also, the ComTrade files that are developed are generated by the RTDS we're talking about 5,000 here. We can take 15 of the ones we feel are the most appropriate, say, in our case, and then provide them to the field station testers, and they'll go, when we're commissioning our relays for installation, and apply those faults, and it's going to basically prove our communication scheme, because we fully expect that to work out. And that concludes my presentation. Any questions?
Any questions?
There's going to be a second chance. That looks the
Oh yes, thanks Vahid, you prompted me. I will be presenting the full paper in just over a week at Texas A&M. So if you happen to be in College Station, I'll be there. Thank you.